So this week we'll be talking about an introduction to study design, and we'll talk about case controls, cross-sectional studies today, and we're also going to talk about ecological study design. So let's review the progression of epidemiologic reasoning we discussed in week 1. Epidemiologic reasoning begins with a suspicion that a factor influences disease occurrence. This can arise from information from clinical practice, from lab research, by examining disease patterns, or by examining prior epidemiologic studies. The next step in epidemiologic reasoning is to formulate a specific hypothesis. Next, we can conduct an epidemiologic study to look at the relationship between an exposure and disease. Within the framework of the epidemiologic study, we must consider chance, bias, and confounding when interpreting study results. We will cover these concepts in depth over the course of this summer. The final step in epidemiologic reasoning is to judge whether an association is causal. We will talk about causality as we go through the semester as well. So the first step in the research process is generally selecting the topic and identifying a research question. This research question is often translated into a research hypothesis after reviewing the current literature about the problem. The hypothesis is a statement that states the predicted relationships between variables. In other words, a hypothesis is a statement of what we expect to see in our study. A hypothesis should be specific and describe how the researcher believes the variables are related or influence each other. Hypotheses are generated using information from multiple sources, including prior studies found in the literature, differences in rates of disease across groups and across time, as demonstrated through vital statistics and through exploring analogous diseases. Once a hypothesis is formed, epidemiologic research methods can be used to test these hypotheses. Well-written hypotheses are specific. They clearly state the predicted relationship between variables. They are also testable. There are research methods that are available to test the hypothesis. They are unambiguous, and more than one answer must exist. Study designs differ in a number of factors, including the number of observations, the directionality of the exposure, how and when the data is collected, whether the data is collected at the individual or group level, and how subjects are enrolled in the study. Epidemiologic studies can be classified as either observational or experimental. Each design represents a different way of harvesting information. Selection of one over another depends on the particular research question, concerns about data quality and efficiency, and practical and ethical considerations. The majority of epidemiologic work takes place in the realm of observational studies. However, much epidemiology and health services research is classified as experimental. Observational studies do not involve any investigator manipulation. There is no random assignment to groups, and researchers must use naturally occurring groups for comparisons. Descriptive studies describe the occurrence of disease in a population. Analytic studies actually examine the relationships between health status and other variables. Experimental studies involve the randomization of subjects into groups, while observational studies do not involve randomization. Now, true experimental designs involve investigator manipulation as well as the random assignment of subjects to treatment groups. Quasi-experimental studies are similar to experimental studies in that the investigator applies the intervention, meaning that they manipulate the independent variable. Where they differ, however, is that quasi-experimental studies do not involve random assignment to treatment groups. There are two main time dimensions, cross-sectional and longitudinal. A cross-sectional study involves assessing subjects at one point in time, while a longitudinal study follows people over time. There are numerous types of longitudinal studies. These include prospective studies that involve identifying subjects and then following them forward through time. Retrospective studies, which identify subjects and then look back in time, typically through the use of secondary data. In time series studies, participants are sampled at different points in time, typically at baseline, after treatment, and at another follow-up. Trend studies look at variables over time, but do not attempt to sample the same people. For example, a study might examine trends in car accident mortality over time in a particular geographic area. A cohort study, however, follows a group of people over time. Now, Frist describes 7 factors that characterize study designs. These include who manipulates the exposure factor. In an observational study, the exposure is not manipulated by the researcher. In an experimental study, the exposure is manipulated by the researcher. How many observations were made? In some cases, observations of subjects may be made only once. However, in other cases, 2 or more examinations may be made. Directionality of the exposure refers to the measurement of the exposure relative to the measurement of the disease. A retrospective approach is where the researcher obtains information about exposures that occurred in the past. A single point in time approach assesses both exposure and disease status at the same point in time, while a prospective approach assesses exposure before assessing the occurrence of disease. Data collection methods refers to whether the investigator is using existing, which also known as secondary data, or if new data must be collected. Timing of the data collection is important in that some studies, information is collected about exposures that occurred in the past. If long periods of time have elapsed between the measurement of exposure and the occurrence of disease, questions might be raised about the quality of the data. The unit of observation can be the individual or the entire group. Finally, certain classes of subjects may not be available for epidemiologic research. Now here you can see a pictorial demonstration of the various epidemiologic study designs. This is an excellent resource to draw on when trying to remember the similarities and differences of various study designs. The 2x2 table is the foundation for epidemiologic analysis. In most analytic designs, investigators are attempting to examine if a particular exposure is associated with a particular disease state. To do this, it is helpful to classify people in a table by their disease status and their exposure status. We will return to the 2x2 table later in the lecture and throughout the semester. The important thing to note at this point is that it is traditional to have the disease status in the columns of the table and the exposure status in the rows of the table. If you always set up your 2x2 tables in this manner, the calculation and interpretation of your measures of association will be much easier. Now, most epidemiologic studies use the individual as the unit of observation. However, ecological studies are different in that the unit of analysis is the group, not the individual. For example, groups that are selected for an ecologic study might be the residents of a particular geographic area, such as census tract or counties. In an ecologic study, information about both exposures and outcomes is collected at the group level. For example, you could research the relationship between the distribution of income and mortality rates between states. So why would we conduct an ecological study? One reason is that individual measurements might not be available, but group-level data can be obtained. Ecologic studies are helpful in revealing the context of health and can help generate hypotheses for individual-level studies. The ecological fallacy is defined as when an association observed between variables at the group level does not necessarily represent the association that exists at the individual level. So this is basically saying you cannot make statements about individual level associations based on aggregate level data. Now, there are some advantages of ecological studies. These include that they provide information about the context of health. And ecologic studies can be performed when individual level information is not available. Finally, ecologic studies can be conducted rapidly and with minimal resources. Some disadvantages of ecological studies include the ecologic fallacy and imprecise measures of exposures. Now, descriptive designs use theory to frame what constructs and relationships need further exploration, description, and definition. These designs do not require a statement of hypotheses. You are simply describing what you see. These designs rarely control for other variables and do not involve any investigator manipulation. Now, correlational designs use non-experimental methods to test theoretical models. Therefore, they are deductive. In correlational research, you attempt to control for extraneous variables through how you select your sample or through statistical means. These designs also do not have any investigator manipulation. Exploratory designs are theory-generating designs. They're never confirmatory designs. These designs may be qualitative or quantitative. They may be inductive or deductive. But again, there is no investigator manipulation in an exploratory design. So let's take a closer look at observational designs. They are the foundation of epidemiologic research. The three broad types of epidemiologic designs are the cohort study, the case control study, and the cross-sectional study. Please note that all three of these types of studies are correlational designs. So which study do you choose? In theory, it is possible to use each design to test a hypothesis. In practice, the choice of study design depends on a number of factors, including the state of the knowledge, the frequency of exposure and disease, time, cost, and other feasibility considerations. Each study design has unique and complementary advantages and disadvantages. Now, in general, a case control study can be defined as a method of sampling a population in which cases of disease are identified and enrolled, and then a sample of the population that produced the cases is identified and enrolled. Subjects are defined on the basis of the presence or absence of a particular outcome of interest. Exposures are then determined for the individuals in each group. Case control studies are often the first formal approach to deciding whether a possible risk factor may be the cause of a disease. Case control studies begin with individuals that have the disease of interest. These are your cases, and then a comparison group of disease-free controls. And then researchers take a look back in time to assess the exposure status for the risk factor of interest. In case control studies, you are really identifying the odds of someone being exposed to the risk factor, given that you know they already have the disease. So when should you conduct a case control study? When exposure data are expensive or difficult to obtain, when the disease is rare, for example, studying risk factors for birth defects, when the disease has a long induction or latent period, for example, cancer or cardiovascular disease, when little is known about the disease, for example, early studies of AIDS, and when the underlying population is dynamic, for example, if we were studying breast cancer on Cape Cod. Now, cases are identified first when designing a case control study. It is important to have a very specific operational definition of a case for inclusion in the study. The criteria for the disease being present must be both sensitive and specific to avoid misclassifying those as having the disease when they do not. We want our cases to be actual cases of disease. Now, you may use prevalent or incident cases. However, incident cases are preferable as they help distinguish between cause and effect. Most importantly, you must select your cases based on the operational definition of a case, not based on their exposure status. Ideally, cases in a case control study should include all persons of a specified population that develop the outcome of interest during a specified time period. However, it is rare to be able to identify all cases, so we must rely on a sample of cases. Cases give you the numerator of the rates of disease in an exposed and unexposed groups being compared. So where are we getting the denominators? We get the denominators from the controls. The purpose of the control group is to estimate the frequency and degree of exposure that would have taken place in cases if no exposure disease association exists. So it's sort of like a background level of exposure. Controls should be chosen from the same population as the cases, and they should be selected to match the characteristics of the cases. It is also very important that you measure your exposure or risk factor in the controls in the same manner that you used for the cases. So where do you find your cases? Many times, cases are identified using existing surveillance or registry systems. Sometimes cases can also be identified from specific hospitals or providers. However, when using hospital cases, you may only be identifying the most severe cases. Therefore, your sample might not be representative of the population as a whole. Now, ideally, we want to identify controls using the same mechanism we use to identify the cases. There are three main ways to identify controls. Now, the general population controls are most often used when cases are selected from a defined geographic population. Hospital controls are used most often when cases are selected from a hospital population. And finally, special control groups like friends, spouses, siblings, and deceased individuals can also be used. However, these special controls are less frequently used than general population or hospital controls. Now, sources of general population controls include random digit dialing, residence lists, and driver's license records. Advantages of general population controls include, because of the selection process, investigators usually assured that these general population controls come from the same base population as the cases. Now, there are some disadvantages to general population controls. They're time-consuming, expensive, and hard to contact and get cooperation with sometimes. And they may remember exposures differently from cases. Hospital controls are used most often when cases are selected from a hospital population. For example, if we were doing a study of cigarette smoking and myocardial infarction among women, we might use hospital controls of women that didn't have a myocardial infarction. So some of the advantages of hospital controls include the same selection factors that led cases to the hospital, led controls to the hospital. The hospital controls are easily identifiable and accessible, and so are less expensive than population-based controls. The accuracy of exposure recall may be comparable to that of cases, since the controls are also sick. And they may be more willing to participate than population-based controls. Some of the disadvantages include that since hospital-based controls are ill, they may not accurately represent the exposure history in the population that produced the cases. And hospital catchment areas may be different for different diseases. So what illnesses make good hospital controls? Those illnesses that have no relation to the risk factor under study are the preferable illnesses for control groups. For example, should respiratory diseases be used as controls for a study of smoking and myocardial infarction? Do they represent this distribution of smoking in the entire population that gave rise to the cases of myocardial infarction? Probably not. Now, special control groups may include friends, spouses, siblings, and deceased individuals. These types of control groups are rarely used. However, when they are used, cases may have the ability to nominate appropriate controls because they have cases may not be able to have the ability to nominate appropriate controls because they have few appropriate friends, they're widowed, or they are only or adopted children. Dead controls are tricky to use because they are more likely than living controls to smoke and to drink. Now, for the Wood criterion, we ask ourselves, if a member of the control group actually had the disease under study, would that person be considered as a case in your study? Because we want controls to be a sample of the source population that gave rise to the cases. The purpose is to provide information on the exposure distribution in the source population. So there are numerous ways to identify information on exposure status. Generally speaking, objective measures are less prone to bias than measures that are more subjective. You may wish to use existing records, interview the cases and controls, use direct measurements, or use proxy measures. An example of a proxy measure would be to interview the spouse or the parent of the case. You must ascertain exposure status the same way for both cases and controls. So if you're using proxy measures for cases, you need to use proxy measures for controls as well. Now, when we're looking at a case control study, it's helpful to walk through an example. So if we were to examine the relationship between dietary vitamin A and lung cancer, we would begin our study by identifying patients with lung cancer, and then we would identify separate acceptable controls that do not have lung cancer. We can then ask participants to retrospectively determine if they had adequate vitamin K consumption. Case control studies can be used to study low prevalence conditions and diseases with long induction or latent periods. They are also relatively quick and easy to complete. They're usually inexpensive, and you can evaluate numerous risk factors at one time. Now, case control studies are inefficient for rare exposures, and they are vulnerable to bias because the measurement of exposure may be inaccurate due to the retrospective nature of the study. Additionally, the temporal relationship between the outcome and risk factor may not be able to be ascertained, and the study design provides indirect estimates of risk. Now, cross-sectional studies measure the prevalence of a disease. In a cross-sectional study, exposure status and disease status are collected at the same point in time. In this study, you are able to indicate an association between variables, but you are not able to establish the temporality of the relationship. In all research, you must identify which variable you believe explains some phenomenon or outcome. The variable that is the outcome, and any other variables that might influence the relationship between your explanatory variable and that outcome. In epidemiologic research, your independent variable is your explanatory variable or your predictor variable. It's the variable you believe explains or predicts your outcome. The dependent variable is your outcome variable. It is the variable you believe can be explained by or is influenced by your independent variable. You can keep these two straight by remembering that you are trying to show that the dependent variable is in fact dependent upon the independent variable. Now, we'll talk more about effect modification and confounding later in the semester, but for now I would like to introduce these terms. A moderating variable is a variable that alters the strength of the association between two variables. For example, let's say that intervention X reduces cardiac readmission rates, but only for patients that are younger than 65 years of age. In this example, age is your moderating variable. Now, confounding occurs when the relationship between two variables can be explained by the presence of a third variable. For example, there's a strong association between alcohol use and lung cancer. However, this association disappears when you take into account smoking. Smoking is a confounder in the relationship between alcohol and lung cancer. So the odds ratio is defined as the ratio of exposed to non-exposed in the case group divided by the ratio of the exposed to non-exposed in the control group. Now, your odds ratio gives you the odds of having the exposure given that we know you already have the disease. Now, the odds ratio is not the same as the risk ratio that we will cover when discussing cohort studies. However, when you're dealing with rare diseases, the odds ratio will approximate the risk ratio. Rare diseases generally means less than 10% of the population have that particular disease. So let's talk about the odds. The odds of being exposed in the disease group is A over C. The odds of being exposed in the non-disease group is B over D. So the odds ratio is equal to the odds of being exposed, given that we know you have the disease, so the odds of exposure in the disease group, divided by the odds of exposure in the non-disease group. So A divided by C over B divided by D. Now, just like the incident rate ratio and the cumulative incidence ratio that we talked about last week, the odds ratio is a ratio measure of association. So let's go ahead and go through just a quick little example. Here we have the odds of being a smoker in the lung cancer group. That's A over C. So the odds of being a smoker, smoking is our exposure, so we take the lung cancer group, and so the smokers in the lung cancer group, there's 50, divided by the non-smokers in the lung cancer group. which is 15, and that's the odds of being a smoker in the cancer group. Now, the odds of being a smoker in the no lung cancer group is the number of smokers in the no lung cancer group divided by the number of non-smokers in the no lung cancer group. And if we want to look at the measure of association, if we want the odds ratio, we take the ratio of those two numbers, and here we get an odds ratio of 11. Now, I want to point out that these numbers were made up for illustrative purposes. This is not the true measure of association between smoking and lung cancer. But besides that, let's talk about what we would mean if we had an odds rate, what it would mean if we had an odds ratio of 11. So the interpretation of the odds ratio is the odds of having the exposure given that we know you have disease divided by the odds of exposure given that we know you don't have the disease. We interpret our odds ratio that the odds of being an odds ratio of 11, that the odds of being a smoker among people with lung cancer are 11 times higher than the odds of being a smoker among people without lung cancer. So this is exactly how we would interpret this odds ratio. The odds of being a smoker among people with lung cancer are 11 times the odds of being a smoker among people without lung cancer. And as I said, this data was made up. So how strong is the relationship? Although there's no industry standard, odds ratios and risk ratios, which we'll talk about next week, are often classified in the following categories. So an odds ratio between 1 and 2 is considered a weak association. Between 2 and 3, a moderate association. Above 3 is considered a strong association. And between 0 and 1 is considered a protective effect, because that would mean that the odds of being exposed in the disease group are actually less than the odds of being exposed in the non-disease group.